Recording in progress.
Okay, cool. Let's get started, everyone. So as you might be able to tell, we don't have a guest speaker today. We were going to have one, but he had to reschedule. So hopefully that'll happen in the next week or two. But today you just have me, unfortunately. Okay, so a few quick announcements. Homework 2 is due tomorrow. We did add Monday office hours, so Joe's going to have office hours this evening over Zoom. We're going to have quiz 2 on Wednesday. So it's going to be just like last time. It's going to be released on Wednesday, and it's going to be due Friday or due Sunday night, I believe. Same thing as last time. It will be about 7 or 8 questions. You'll have an hour, so on. We'll release homework 3 probably by Wednesday, maybe like by Thursday at the latest. But hopefully, no one's going to be super mad about like a day late or something. And a few people asked, so quiz 1 of answers are available on Canvas. I think if you just navigate to the quiz page and you can see the answers. I'll remove those in a few days. So if you care about looking at the answers, please do so soon. Any questions about logistics? Okay, cool. Any questions about last time we ended the recommendations module. Are there any questions about recommendation systems before we move on to pricing? Okay. So let's start with pricing. So what are we going to do this entire module? So we're going to start with just the basics of pricing and algorithmic pricing. And so today's class is actually going to be so for those of you who are in the OR program or with an OR background, this entire module is probably the most similar to what you would learn in a traditional sort of OR class like revenue management. We are going to be focusing more on the algorithmic and programming and data side as opposed to like the theory side. So like we're not going to ask you to like prove things or derive optimal pricing or things like that. We're just going to show them to you. If that's what you like, sort of there's classes next semester that are going to sort of cover very similar topics, but partially in similar ways, but partially with a different focus. But today is almost going to be like exactly how an OR class would introduce would introduce pricing. And in particular, we're going to be talking about pricing under uncertainty for what people like, or if people have heterogeneous valuations. Heterogeneous meaning just people have different valuations. And then we're also going to be looking at demand estimation. So how do you estimate how much demand there will be at a given price? And then starting Wednesday, we're going to be talking about challenges from practice. So just like we did for recommendations, so it's going to follow a very similar structure to recommendations. Today is the foundations, the basics. And then starting Wednesday, we're going to be talking about capacity constraints, dynamics, competition, selling multiple items, and things like that. Some of this is also what you would see in a traditional operations class, like a service systems or revenue management class. Some of it, the focus will be quite different. And then next week, we're going to depending on when the guest lecture gets rescheduled, but at some point we're going to discuss quite an extended case study on pricing in online marketplaces, and in particular pricing, for example, in ride-hailing marketplaces. And so there you have all sorts of things like real-time pricing, spatial pricing, like different locations at different times. You have look-ahead pricing, like you always know that rush hour is going to be busier and more expensive, and things like that. And then this is a lecture that I really like, or what I'm really going to be excited for is we're going to sort of have a lecture on, that'll be far more interactive. I actually stole it from an MBA class that I happened to sit in on a few years ago. But so there will be like discussing different questions on when algorithmic or dynamic pricing might be ethical or unethical. And this class, I'm not sure exactly when it'll be scheduled yet, but it would be great for everyone to be here in person. It's really hard to have. It will be really hard to have this class remotely. Okay. So Any questions on the outline on pricing before we dive in? Okay. So before we talk about pricing, let's just a little bit introduce what we're going to assume about users for basically this entire module. It's of course going to be very simplified, but it's a useful starting point. So right now, today, we're going to be even more simple than what we're going to expand to next time. But for now, let's just assume that you're selling one type of item. So you have, this like food item that you're selling. You don't have any other item. You just have that one item, and you have unlimited copies of that item, so you don't have to worry about capacity constraints. We're going to say that each person has a private valuation VI for that item. So that's how much they value it in terms of dollars. And then suppose you're selling a copy of that item for price P, right? So you have some price that you're just offering to sell it. You have it up on a sign. And then each person is going to look at that price and make a decision to buy it by simply comparing their private valuation that they know but you don't know. And they're just going to compare that to the price. And they're going to buy it if their valuation is greater than or equal to the price. And then if let's say you care about maximizing your revenue, so like how much money you earn, then it should be sort of, you should be able to see that the way you do that is if you knew the valuations, then you would just set, for each person, you would set the price exactly equal to their valuation. And the way to see that is if you set the price more than their valuation, then you don't make any money because they don't buy it. And if you set the price to less than the valuation, you could have made more money by setting it to exactly their valuation. And what I want to emphasize here is sort of this is like the most simplistic model possible. We're not thinking about like any behavioral effects or like negotiations. We're not thinking that your price might anchor them into believing what their valuation is. We're not thinking about other items affecting their opinion. It's just one item. They have some valuation that comes from somewhere, and then this is what happens. Are there any questions about this setting? Because sort of this model is going to, or variations of it are going to carry through this entire module. Okay. Okay, so we have a model. We have, of course, like a hammer of machine learning. So it should be fairly easy to just like sort of why are we spending 3 or 4 lectures? This should be fairly easy, right? So if I know what the optimal thing to do is, I know like optimally what I would do is I would set price exactly equal to the valuation. So what's maybe the second best thing one could try first? Of course, the challenge is that we don't know the valuation VI for each person. That's unknown. But like that doesn't seem like a hard challenge, right? In the recommendation context, we also didn't know the valuation for each person and each item, but we could use past data to estimate those valuations. And we talked about a lot of tools to estimate valuations. So maybe this isn't too hard of a problem to solve, right? Maybe I just use a machine learning approach and I create an estimate V hat for the valuation of each person, and I use historical data and then k-nearest neighbors and regressions or matrix factorization, everything that all the toolkits that we learned for recommendation, and like that stuff just worked in recommendations, right? Okay, and then I set the price to set the price exactly equal to the valuation, because if my machine learning model is perfect, then that's the right thing to do. And it's not perfect, but no model is perfect, and so let's just pretend it's close to perfect and set the price equal to that. Who thinks this is a good? I mean, maybe I'm revealing it too much, but like, who thinks this is a good idea to do, or like, this is like a fairly reasonable thing to try first, right? Sort of, does anyone think why or have ideas for why this might not work? So sort of, yeah, the punchline is like this approach is going to miserably fail if this is what you do. And what I emphasize is this approach doesn't miserably fail in the recommendations context, right? Sort of, this is exactly the approach you did. You just estimated ratings, Rij, and then you just, without capacity constraints, you just recommended the top rated item. So does anyone have an idea for why this approach would fail in the pricing context? Okay, so the question is it doesn't, or sort of the guess is it doesn't consider the price of other systems or comparable products. So I mean, yes, it certainly doesn't, but like even in the very simplistic model that I showed with a single user, a single item, no competition, just in that model, my claim is that this approach fails. Okay, so the answer is you can't, or sort of the guess is that you can't set different prices for the same product for different people. Let's pretend you can. And I think I heard, sorry, your head next. So the claim is you're going to anger people. Okay, let's pretend you don't anger people. Okay. Yep. Great. So that's the answer I was fishing for. So the answer was that sort of the actually I'll just dive into it. So okay. So let's pretend your sort of your estimated value vi hat is not perfect. So like suppose the true valuation is 10, and what is my revenue if I estimate 9? And I set the price to 9. Yeah, so my revenue is 9, right? They sort of, the price is less than their valuation, and so they buy it, and I earn $9. But what is my revenue if my guess is 11, and so I set the price as 11? 0, right? So there's, like in the basic model, there's a discontinuity in guessing too high and guessing too low. And so small errors in guessing the valuation can have huge revenue implications. Are there any questions about that? All the other answers that people gave are also great, valid reasons. But yeah, and we're going to be talking about a lot of those later on in the class, or later on in the module. Yeah, so the question or the comment was that even if I can estimate the hat I very well from like using past data, maybe estimates are changing over time. There's like dynamics and so on. Yeah, so I think that's a great point, and that certainly makes like this approach even more infallible. Is that you're really trusting that this works. Yeah, and so sort of two final comments here. I think one related to what you just said. So the first one is that you need to incorporate uncertainty in your pricing decisions. So in the recommendations context, we could just take what's called the point estimate, just like the estimate of the rating, and we knew that our estimate's not perfect, that there's noise around it, but we didn't care. But here in pricing, we have to care about the uncertainty around my pricing guess. And then I think sort of related to what you just said is, and we'll get to this later on in the class today, is you also don't have great data to actually estimate the valuation exactly. Because like think about what data you have. The data that you have is like in the best case is a bunch of pricing decisions, is a bunch of purchase decisions people made in the past. no one has ever told you what their valuation is. All you see is a bunch of observational data that you gave the value, that you offered some price, and then they either purchased or not. And so you see a censored version of the valuation because you only see a binary, is it greater than or less than some price. And then once on top of that, we add on dynamics, like valuations can change, opinions can change, then it just becomes really hard to estimate BHAT exactly. Are there any other questions here? Comments? Okay. Okay, so let's talk about optimal pricing with uncertainty. And yeah, this is, yeah, okay. And so what we're gonna cover here is, in the revenue management literature, is what's called posted price mechanism. So I just post one price to everyone. But the math that at least we're gonna cover today under the simple model is basically the same if we also think about personalized prices for each person. Okay. So what's the challenge? I mean, we've been talking about it so far, is there's a lot of randomness in whether someone purchases at a given price, right? And there's, I think, two high-level ways to think about this randomness. The first one is that you have a single price P for the entire population, and people differ in how much they value the item. So maybe someone has a valuation 20, another person has a valuation 5. And then if a random person shows up today, then like their valuation can either be 20 or 5, and there's randomness in that. And I have to give one price such that I have to post the same price for either the 20 or the 5, and there's randomness in who shows up. Another way to think about it is you are doing personalized prices. So you do have a price for each person, but you have uncertainty in your estimate. So your estimate for the valuation is not perfect. So you think that, you know, with some probability this person's valuation is 20, with some probability this person's valuation is 5. And you can think about that like, of course, there's entire classes that talk about standard errors in estimating values in machine learning models, but you can think about that, like one way to think about that is in a regression context. You have a standard error around your coefficient or around like how accurate your estimate is, right? And so the math that we're going to talk about today is the same whether you're thinking about the randomness as across people or randomness in your estimate. Or, sorry, I'm being very, for those of you familiar with Bayesian versus frequentist statistics, I'm being very slippery when talking about whether the valuation is random or whether my estimate of the valuation is noisy. I'm going to be using those interchangeably. I just want to give a caveat that those are not the same thing. I'm happy to talk about it offline, but it's not that, ignore that caveat if that didn't make sense. Okay, so why is this a problem? Okay, so I think we've already talked about this. In recommendations, we ignored noise. So we just took the point estimate. We just said, I have some valuation VI, and then I just sorted by the valuations, and then I just went from there. And the reason I could do that, so it turns out even in that context, it's not perfect to do this because different items can have different amounts of noise. But let's ignore that. Like why was that mostly okay in the recommendations context is because it's fine if you're a little bit off, right? So if you have two items that sort of if you have one item that's you predicted a 5, but it's actually 4.8, and another item that you predicted 4.5, but it's actually 4.9, it's like, yes, you like technically recommended the wrong item, but the true valuations were close to each other. So as long as your estimates are not too noisy, you might be recommending the wrong items, but the true valuations are still going to be similar. And so there's not that much error as a consequence of the noise. But here, sort of that noise is crucial if we want to think about maximizing revenue in an expectation. Any questions here? Okay. Okay, so let's talk about the model. So for at least the next few slides, I'm gonna, even though there's multiple similar ways to think about the valuation, for now I'm just gonna think about, let's suppose you're posting a single, and I'm gonna talk everything in this context. Let's suppose we're posting a single price for the entire population. And let's say we have unlimited copies of the item, so we don't have to worry about capacity constraints. Okay, and so just to make that clear, so one consequence of this unlimited copies of the item is decisions are not coupled across people, right? Each person that comes in, I can just think about maximizing revenue from that single person, and I don't have to think about, okay, but if I sell to this person, what does that mean for the person that comes tomorrow? And so this boils down to thinking about like single person, single item maximization of revenue. Okay. And so suppose I know, or like suppose, so in the second half of this class, we're going to talk about estimating a distribution. But suppose I have a distribution F of the user's valuations. And so this is just a histogram of, this is just like, this is, for example, normal distribution of like how much people value this item. And so the mean is 5, and there's, I think the standard deviation in my simulation was 1. And this is and let's suppose that we know that this is the distribution across people. And so what happens if we set a fixed price P? Each individual with one sec, let me try to lessen the lights a bit. That did the opposite. Okay. So yeah, so if I set a single price P, then each individual with a valuation above P buys it. And so sort of in this plot, everyone in green, like everyone with valuations in green buys the item. Anyone with valuation in blue doesn't buy the item. And so sort of if lowercase f of v is my probability density function for the item and uppercase f is the cumulative density function, do those terms make sense to people? Anyone want me to? Okay, great. Yeah, so please tell me if those terms don't make sense, because we're going to be using those a lot for the next few classes. Yeah. So okay. Yeah. So the density f of v is, you can think, so in a discrete so let's say we have a discrete distribution. The density lowercase f of v is just the probability that I'm at each value. So it's equal to the probability that my price is 5, equal to the probability that my price is 6, and so on. In the continuous context, you can't it's called a density as opposed to sort of like a mass. But yeah, so this is the sort of the density lowercase f of v, and then you can also integrate that. So uppercase f of v is what is the fraction of people that have valuation v or less, right? Or just f of p is going to have the fraction of people with valuation p or less. And what I've plotted here is not f of p, but 1 minus f of p. So what is the fraction of people? So for each p, for each price, what is the fraction of people with valuation at least p? And the reason I did that is because that's exactly the fraction of people that purchased my item at price P. And so I'm going to call D of P, I'm just going to set D of P as what's called the demand at price P, and it's just equal to the fraction of people that are going to buy the item if I set the price to P. Or if I'm thinking about the individual, sort of pricing individually and noise around the individual's sort of value, my estimate of the individual's valuation, then you can think about D of P as the probability that that individual buys the item if I set the price at PI. Yeah, so yeah, exactly. So the reason you care about, okay, so the reason you care about the what's called the CCDF, the complement of the cumulative density function, so 1 minus the CDF, is because so in this plot, everyone in green, everyone in valuation in green purchases the item, right? So if I price it at a 6 and you value it at a 7, you're going to buy it. If you value it at an 8, you're going to buy it, right? So if I price it at 6, anyone with a valuation above 6 buys the item. And so this plot, the sort of the complement of the CDF is just the sort of the mass of this green part as I change the price, right? So as I sort of so this is at price 6, and so this is, I'll show this in the next slide, but it turns out around 6 is around 20% of this plot. Yeah, so the likelihood that their valuation is above the price. Yeah. Oh, so this means it's distributed according to F. So this means that the valuation of VI, so VI is a random variable, and the distribution of the random variable is according to the distribution described by F. Yes. So uppercase F is a distribution. Yeah, and so this is the the probability density function of that distribution. Yeah, so we're going to talk about that quite a bit later on. Okay. Okay, so what is the expected revenue? Okay, so now if I set the price to P, the demand at price P is D of P, which is equal to 1 minus F of P. And so what is, like, how much money do I earn on average if I set the price to P? How much money I earn on average is the revenue I earn from each sale times the probability that that sale happens, or times the demand at P, right? So that's my expected revenue is P times 1 minus F of P. And so another way to visualize that, so this is the same 1 minus F of P plot as before. And now my revenue is the area of the rectangle, where the rectangle is defined by sort of the price, like sort of my price is 6, and then about 20% of people purchase it. So the height is around 20 or 0.2, and the width is 6. And so my revenue is the width times the height, right? So it's the sort of the area of the rectangle on this plot is about my revenue. And so another way to think about this is, as my price increases, the width of my revenue, the width of my rectangle gets bigger because you're increasing price, but the height of my rectangle gets smaller because you're decreasing the probability that someone buys it. Right, so you earn more money from each sale, but you have fewer sales. And then now you have, and so what I plotted here is exactly the area of the rectangle as or my expected revenue as I increase price. right? So first, it's increasing in price because sort of how much money I'm earning on each sale is more than like how much money I'm losing from fewer sales. But then eventually, the number of sales is going down too much that even though I'm earning more money by more sales, I sort of it's not worth it. Okay, and so the revenue maximizing price is just the price P that maximizes P times the demand. And if we were in sort of like a pure operations class, a pure revenue management class, we would spend a lot of time like sort of solving this optimization problem under different functions F, like taking derivatives and like finding the maximal price and things like that. In this class, we're just going like even in the homeworks, you're just going to like brute force, like you're going to discretize P into a bunch of candidate prices and then just like empirically or just like just calculate the revenue at each price and then take the maximum. So we're not going to talk about optimization here, except that you're going to computationally find the solution. So there's a lot of nice assumptions you can make on the distribution. So if this I mean, so just from here, even though this is a normal distribution, sort of what's nice about this shape, so you're finding the maximum of this shape, right? If you've like taken an optimization class, then sort of there's something nice and something bad about this shape. So the nice part is that it's unimodal, right? That there's like there's one maximum, and sort of there's no local maximum, right? There's just like one global maximum. There isn't like a little bump here. But on the other hand, this is not nice because it's not concave, right? So if you had like a concave function, then that's like relatively easy to optimize. But like this part is not concave. So yeah, so there's assumptions under which this becomes like a nice optimization problem. Any questions about this? Okay, and so my optimal price is the price that maximizes this curve. And my optimal revenue, sort of the revenue at that price, is just the value here, right? So if I set the price to around 4, I get a revenue, an expectation of around 3. So, and that's here, so that would be like a rectangle like this. Someone have a question? Okay. So any questions about this basic setup until we go to personalized? Yeah, so yes, okay, so let's say we were in a personalized context. And so this is my noise for how much, like, let's say instead of V, this is Rij, right? Then there's some value, there's some distribution around my predicted rating Rij, just because like my predictions aren't perfect. And so let's say this is the distribution for one person, right? Then what we effectively did in the recommendations context is just assume that there's no noise, that their valuation was exactly the mean of the distribution. And so the mean, so the mean of this distribution is 5. And so we just set Rij to 5. But if we set Rij to 5, then sort of I would set the price to 5. But it sort of, as we sort of just went through, the optimal price is actually less than 5. The optimal price is around 4. And that's because if I sort of set it to 5, then like even though the mean user will buy it, it turns out I can make more money if I make less money per user, but have more sales. Yeah, great question. So one of the questions, so the question was, is like, how does this work for luxury goods where like part of like the point of the price is like exclusion, right? That like sort of like the value of the item comes from the fact that like you're showing off that you have this item. Or do some of y'all remember there was like I think like an iPhone app like 7 or 8 years ago that like literally you just had to pay $1,000 for the app, and like it was like it said I am rich, that for whatever reason some people thought that was like a cool app to buy, and like they got a lot of sales, right? And literally the app did nothing except cost $1,000, and so the entire value was whatever, telling people that you're rich through an iPhone app. And like that's, again, hopefully no one, I mean maybe someone here's a crypto bro, but like that's what like NFTs are, right? um, is like sort of, it's like artificial scarcity to signal that something. And yeah, so that's we're gonna kind of cover that a little bit in a few lectures, but yeah, so this does not take that into account. Like this is assuming that there's some fixed valuation that doesn't depend on how much I price the item. And you can think of like not just sort of this like artificial scarcity thing, but there's like a lot of other reasons to doubt that, right? Like there's now like 50 years of literature on behavioral economics that if I sort of how much I price something influences people's like perception of the valuation. Like in some sense, that's like all modern art, right? Um, but okay, sorry, maybe that was too aggressive. Okay. Any other questions here?
There's been a couple times you mentioned like noise. Can you maybe give a couple examples of that, or like the normal distribution?
Yeah. So yeah, so you can think about this distribution as like two different ways. One, you can think about this as like each person has some fixed, like sort of each person has some valuation that let's even suppose you can like know the valuation for each person exactly. Like each person's coming in and like not wearing a sign, but like you sort of you can know the valuation exactly. But you're limited to setting one price for the entire population. And so there's going to be noise in which person shows up. Is the person with valuation 20 showing up today, or is the person with valuation 3 showing up today? Right, so that's a source of randomness. Another way you can think about this noise is I have some, I have some machine learning model that like estimates valuations for each person. And that machine learning model says, my estimate is 5, the mean is 5. But there's very like sort of there's noise around the estimate because like the estimate's not perfect, right? There's there's like an error distribution around that noise. And so you can think about this as like the noise of the error distribution. Okay. Any other questions here? Okay, so what would you do with personalized pricing? So far, we've assumed that we have some population distribution F, and we find the single price that maximizes revenue. But you can also, now let's instead suppose that we have covariates for each person. So we have, you can think about demographic covariates, you can think about income, you can think about location, whatever. And you're allowed to give different prices to different people. And so let's not worry about people getting mad. Let's not worry about like legal considerations. Let's just say that we can give different prices to different people. I mean, and this happens all the time, right? Like airline prices that you like search online are a form. You know, I'll talk about this stuff in practice. Maybe not next time, but the time after. But this happens all the time. So yeah, so you can do prices by geography. Like a grocery store in one neighborhood can charge different prices than another neighborhood. You think about student or senior citizen discounts. Okay, and so now, sort of in the model that I've shown so far, in which you have no capacity constraints across people, then you can just decompose the problem into separate problems. So you can say, I have some conditional distribution for how much they value the item, given the covariates. So there's some distribution of valuations given that you're a senior citizen, or some distribution of valuations given that you live in this neighborhood, because those covariates don't perfectly, like there's still going to be noise even after I condition on those covariates. And then you just create a price Px that maximizes revenue for this distribution. So you just solve the same exact problem that I just said to solve, but now you just solve it separately for each covariate type. And this is just the previous equation, but now there's just x's everywhere. Okay, so what's an example of this? So suppose, and we'll also talk in this example. Hopefully, it will be clear like why you want to do this, right? So suppose you have a binary covariate, and the population is evenly split for zeros and ones. And let's say that the distribution of valuations differ by the covariate. So now everyone with the covariate 1, sort of the distribution of the covariate 1 is in green, and the distribution for the covariate 0 is in blue, right? So there's so the population distribution is sort of the combination of these distributions, but the conditional distribution is just either the green or the blue. And then, of course, purchase probabilities at each price is also going to differ for the two. And so what I have here is get the 1 minus the demand for the green, the demand for the blue, and the combined demand. Right, and so sort of I've already said this. If we don't have any capacity constraints, we can just solve the problem separately for each group. Yeah, so this is the optimal price for the blue group is 4. The optimal price for the green group is like 6.5. If I set just one price overall, then I would set a price around 4.25. Yeah, so like let's suppose I have unlimited copies of the item I want to sell, right? And so the reason that and we're really going to talk about capacity constraints next time, but suppose you just had one copy of the item to sell. Then just like in recommendations, where if you had just one item, one copy, then you want to like shade the like the score function sort of should like normalize by the average rating, right? So in the recommendation context, we said if I only have one copy of the item, you better really, really like it if I'm going to give it to you. Just like liking it about average is not enough. And so here, it's going to be sort of here, and we're going to talk about this next time, is if you have just one item to sell, then you better really value it. Like I better sell it to you at a high price, because if you don't buy it at a high price, someone tomorrow will come in and buy it. Okay. And so what's in this simple example, what's the value? What's like the benefit from personalized pricing, right? So if I in this example, if I do the revenue from the single price is the brown line, is sort of the height of the brown line, and it's 3.8. And the revenue from the separate prices, so it's actually not on this graph, but it's 1/2 the revenue from the green, because they make about half my population, plus 1/2 the revenue from the blue, because they make half the population. And so my revenue from separate prices is about 4.7. Right? So I didn't eliminate all noise by conditioning on the covariates, but sort of I reduced the noise. Sort of I have 2 separate distributions, and I price separately, and then I gain something. And then things get more complicated if there's capacity constraints. Things also get more complicated, and I'm going to touch on this next time as well, is so in this example, we assumed that we knew someone's covariates, right? So we assumed like someone comes in and they show their student ID or their senior citizen or their ID with their age. But what if sort of people don't come in with their covariates, but you know that there's like sort of some people who really value an item and some people who don't. So for example, in ride hailing, some people really want like a ride right now, right? Like they want to, like they're time sensitive, they like want to get to where they are right now. Another person might be willing to wait 10 minutes if that saves them $3, right? So some people will value time over money, other people will value money over time. And so there, in that example, you can like, and we'll talk about this next time, is you can offer them 2 separate products, right? And Lyft basically does this now. They offer a product that's you get a ride immediately and you pay more, or you get a ride sometime in the next 15 minutes that's convenient to Lyft and you pay less. And so you're not asking people directly like whether they have a high valuation or low valuation. You're just providing multiple products at different sort of, yeah, at different quality levels. Okay, so any questions about optimization, about finding the optimal price? I'm not going to move on until there's a question. Also because I want water. Yeah, exactly. Yeah. So the question is should you like, can you use this for, or is this used for like marketing decisions? And completely, right? So there's some cost to splitting prices by market, right? There's like either just like a logistics or like data scientist cost that it's just like harder to do this for different segments. Or like do different like Trader Joe's has different prices per neighborhood. It's just like it requires some amount of overhead to create those prices. And there's the question of how much like benefit is there, right? And so if you like do this analysis and you realize there's not like I don't earn that much more money by pricing differently, then like why bother? Great question. So that's exactly what we're getting to. So the question is like, why can't we machine learn the distributions? And that you can and you have to, and that's what we're going to cover next. Sort of the challenge is that you can't machine learn, or you don't want to directly machine learn like this, like the mean value per person. But rather, you want to learn something slightly different that we'll get into next. Any other questions? Let me just make sure that, okay, great. Like worried that it wasn't recording for a second. Okay. Okay. So yeah, so let's get into learning the demand distributions. So, okay, so far what we've talked about is calculating optimal prices if you knew f of p, so if you knew the distribution, or if you knew the conditional distributions. Of course, the challenge is you don't know these distributions. You need to learn it from data. And so what does the data look like? This is actually just a screenshot of the data frame that we give you in the homework. So what is it? What does what is in most settings your data look like? You have each row is a customer in the past, and you have some covariates. So maybe you have location, maybe you have income, and then you have the price at which you offered them the item, and then you have their decision for whether they purchased. So you never have data on their exact valuation, right? At best, you have data that looks like this, where you have a bunch of people with their covariates, then you have some offer, and then their decision. And so this is an example of censored data, right? So all you observe is if their valuation was greater than, for the first person, 4.7, or if their valuation was greater than 0.61. And so the task is we want to learn the distribution f of p, or the conditional distribution conditioned on covariates using data that looks like this. Okay, and the assumption for this entire module that I'm not going to touch in this entire module, and it's a huge assumption. It's almost never true in practice, and there's a lot of revenue management literature on how to get around this assumption. But for now, for this entire time, I'm going to do like the huge assumption that we see past decisions at many prices p, right? So that in the past, I randomize prices to a bunch of people. And like the only way that's almost never true. And the only way that's true is if you like ran an experiment. And so we're going to talk about experimentation in the next module. And so we'll cover like some things like this. But like think about how pricing decisions are usually made, right? You like find some optimal price and then you show that price, either to each individual or to the population at large, right? And that's a fixed price. You don't do noise. You don't like add noise around the price, and so you never observe decisions at different prices. And as we'll get into, it's really hard to know what percentage of the population would have bought it at price $2 if you've only ever offered the good at $6, right? That's like you just don't have the data to do that. And yeah, so it turns out there's like a bunch of like clever things you can try to do to like estimate distribute. So this is like a form of extrapolation or out of sample sort of generalization, and there's in machine learning, and so you can think about all sorts of tricks you can try to play, but this is a fundamental limitation to basically everything that we're going to cover in this module. Does that make sense? Okay. Okay, so what's the naive approach? This should sort of, the next two slides should seem very familiar. So what's the naive approach? The goal is to estimate demand of P for each price P, and you want to do this for a reasonable range of prices, right? So like, you're never going to get, like, you don't actually, like, you're never going to try to estimate how many people buy this candy bar for $1,000, or like how many people buy the computer for $0. Like, well, you have some reasonable range, and you want to estimate the demand distribution for that reasonable range. So what's the naive approach? Just bin the historical prices offered. So let's say my prices are random. My past prices are between 0 and 4, or like $1 and $6. Then I say bin everything between $1 and $2, 2 and 3, and so on. And then in each bin, just construct the estimate as the fraction of offers in that bin that were accepted, right? So this is empirically the fraction of people that accepted an offer in that bin, right? So my estimate of demand is the number of offers accepted over the total number of offers in that bin. Is that clear why this is why this is a reasonable estimate? Yeah. So my goal is to estimate the demand at price P, and demand at price P is defined as the fraction of people who will buy the item if I sell it to them, if I offer it at price P. Right? So that's the definition of what I want to estimate. And then what I'm using as my estimate is historically, if I offered a price close to P, and so the bin is all the prices close to P. If I offered a price close to P, how many people accepted it in the past? Or what fraction of people accepted in the past? So that's almost a direct estimate of the thing that I care about. Okay, and so when estimating with covariates, just do the same thing, but now do it for every set of covariates separately, right? So, or you can bin continuous covariates and just do this estimation exactly for different sets of covariates. Great question. So the question is, I'll get to that in a few minutes. And so the question was, how do you decide how many bins to use? And intuitively, that should matter, right? So if you use more bins, then if you use more bins, then each bin has a smaller width, right? And so I'm only basing my estimate based on prices close to P, right? So if my bin is from 6 to 6.2, it's fairly reasonable to assume that maybe 0.2 doesn't make a difference in my demand. And so thinner bins are better. But if I do thinner bins, then I have less data per bin. And so this should start to sound familiar to something we've seen in class. Okay, so what I've plotted here is I fixed the number of bins, and I just exactly ran the method from the previous slide with 100 samples, 1,000 samples, and 4,000 samples. Okay, so what are some pros? This is clearly simple to implement. Like it took me a few minutes on a slide to explain. This is what's called a non-parametric assumption or non-parametric approach, which means I'm making zero assumptions on what the distribution looks like. Like I'm not assuming that prices. I mean, besides the assumption that prices are or demand is somewhat continuous near in my bin boundaries, that the demand at 6.1 is close to the demand at 6. But besides that assumption, I'm not making any other assumptions. Right, so I'm not saying that the shape of this curve looks like this, the shape of this curve, it could even be demand could even be increasing in the price. It just no matter what this curve looks like, I'll learn it if I have enough samples. Right, so as the number of samples goes to infinity, this converges to the truth. Why wouldn't you want to use this? So it wastes data. So the only data you're using to estimate each bin is data for that given price and that given covariate, right? But intuitively, if I price something at 10 and they buy it, that should tell me something about if I priced it at 5. And so because it wastes data, it requires a lot of samples. And so what hopefully some of you noticed by now is this is basically the exact same trade-off that we talked about in naive estimation and polling, right? Is we were using, so there we use the empirical mean, or sort of for within each covariate. So even in weighting, what did the naive method for weighting do? We took the empirical mean per covariate group, and then we did a weighted average. But the step of taking the empirical mean had basically the exact same pros and cons here. And so everything that we talked about there about, about like doing too specific of a group, like, using too many covariates, about number of data samples, about bin size, basically all of that just like apply to here. Any questions about the approach? Okay, but then under that view of the world, that this is basically the exact same as naive mean estimation, that should also tell you how to fix the downsides, right? We also had in class, we talked about a method in polling, and there's the exact equivalent method here. So what do we want to estimate? Let's say that we want to estimate the demand at price P given the covariates X. And so that's just what I'm going to use. Oh, sorry, there's a little bug here. This is supposed to be 1 minus f of p. But yeah, so we want to estimate the demand, which is 1 minus f of p given x. Okay, and so in the polling module, we replaced mean estimation with sort of multi-level regression with with MRP, and more generally, just like plug in a machine learning model to do the estimate instead of mean estimate. So now we're going to just plug in a machine learning model to estimate this demand. And there, what we did was we borrowed information across covariates, right? So we said if someone is 50 to 65, that like, and like, the mean is within that range, sort of we have some estimate for the mean for people 50 to 65 that tells us something about the mean for people 65 plus, right? And so the same thing here. Now, what our machine learning model is doing is it's borrowing information across prices and covariates. But the downside of that, we didn't sort of talk about this too much earlier, but the downside of that is now we're making assumptions on how to borrow information across prices and covariates, right? Like my machine learning model is imposing that there's maybe like a linear relationship in income, or like, yes, if you do linear logistic regression, those are imposing different assumptions on the shape of the relationship. And so in the homework, we're going to ask you to do logistic regression to estimate demand. And so how do you just do it? So your target is is logistic regression clear to everyone? Sort of my understanding is for those of you in urban data, today is the first day of logistic regression. So if you don't understand it yet, hopefully you will in a few hours. For those of you in applied machine learning, I have no idea when you cover logistic regression. But okay, I'm just going to assume you know it. Okay, so the target is my purchase decision, so a binary decision for whether this person purchased or not. And then my covariates are the price offered, the user covariate, and then any interaction between price of the covariates or interactions between the covariates or transformations for the covariates. So any questions on how you would do this? Yeah, so the question is could you reformulate it to try to predict the price at which someone's going to purchase something. So the problem with that approach is, so that's exactly the approach that I talked about at the very beginning of the lecture. That if you get the price wrong, if you like overestimate the price, they're not going to purchase. And so that's why we need to go through, first estimate the demand. So it's a two-step process. Instead of directly trying to predict the price, you do a two-step thing. You estimate this demand distribution, and then plug that into an optimization to find the optimal price given that demand distribution. Any other questions here? And there's nothing special about a logistic regression here. Like you can plug in a random forest, you can plug in a linear regression, you can do k-nearest neighbors, whatever you want. Okay. So some like parting comments. So what we talked about today, again, sort of what I said at the beginning of class, today was probably the most traditional operations research lecture for the entire semester. Basically, everything we covered today is something you would also learn in like if you take like for like one lecture if you take service systems in the spring, for example. And the reason for that is this is probably sort of this demand estimation part is probably the most important and difficult challenge in revenue management or setting prices. Like sort of the entire game is finding good estimates of demand distributions. And sort of in class, we've talked about various challenges. So we've talked about like estimates change over time. They're really high dimensional. They like the data that you have is like not really ideal for demand estimation. You need experimentation in the past, right? But at the same time, it's just like a core task to do any pricing, right? Any price that you set is under some assumption on how many people are going to buy the item under your price, and like how much and you want to optimize revenue or profit or whatever, right? So this sort of this is probably the most important, but also the most difficult challenge in revenue management. And unlike in most machine learning challenges, we need to estimate a function instead of estimating just a point estimate. So we need to estimate a distribution. So at each and one way to estimate that function is to treat price as a covariate in a machine learning model. I just want to repeat this. We made a quite substantial assumption that you have historical data at many prices P. And this basically requires a experimentation, right? This basically requires you to do a little bit of exploration for do I set the prices at 5 or 10 or whatever. And like if I was giving this lecture 15 years ago, this would be a much bigger hurdle than it is today, right? So like today, it's like, especially like for like online retail, it's virtually costless to do experimentation or to do even personalized pricing, right? So if I go to like Google Flights and like try to buy a flight to California, like they show me some price. I have no idea if they're showing me if they're showing the same price to someone else, or if they're using my browser cookies. You have no idea if they're like pricing different over time. You have no idea if they're randomizing prices, right? So there's a lot of experimentation going on in prices. And actually, this is also very different than even if I was giving this lecture 2 years ago, because so actually a quite substantial part of the revenue management literature is but this is like a little funny to me that like there's so many people studying this, but it's such an important problem, is like physical menus make it hard to experiment with prices, right? Like you're at a restaurant and they give you a printed menu and there is some cost, like just like physical printing cost to change the prices on the menu because they have to print new menus out every time they do so. And now you have to think about, is literally the physical cost of printing worth your, like how much you're going to gain by like having optimal prices? But and so now there's like some like literature that during the pandemic, sort of like those menu costs have gone away because a lot of restaurants have switched to QR codes. If I'm sending you to a website, it's virtually costless for me to change prices on a website, right? That's just like some HTML that I have to update. And so like you also see like fast food places, like franchises often, instead of like a menu on a board, like a physical board, they'll have TVs for menus. And that's partially so they can change prices really quickly without incurring a physical cost. Yeah, and so we're going to talk a little bit about experimentation in the next module. Okay, so any questions about this?
Is there any way to use maybe historical data for like similar goods that might be priced differently rather than experimenting?
Yes. So the question is can you use similar sort of learnings from similar items instead of experimenting for each item? Yes, and that's sort of everything that we learned in the recommendations context of learning across items basically applies here. And there's a bunch of researchers trying to figure out exactly the right way to do that. Yeah, so totally. So the question is can you simulate, like simulate under assumptions on like what demand distributions look like, or like simulate under, like just like like learn some parameters and then plug it into some like larger model and then simulate. Totally done all the time. Any other questions here? Okay, then sort of the last thing to cover today is like even though we like in some sense covered a lot today, we had to make quite a lot of assumptions on how to get like a clean formulation of how to do optimal pricing, right? You want to sell just one item. You have no capacity constraints across people. You have no competition from other sellers. There's no time dynamics and like how much people value the item. And you're allowed to explicitly give different prices to different users, right? Like this is a lot of assumptions that that basically never hold. And then we said under these assumptions, how do you calculate the optimal price and how do you do demand estimation? And so next time we're going to try to relax some of these assumptions. I think that's sort of all I have for today. Happy to take questions offline.